This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So, in previous sessions, we have discussed about shear forces and bending moment diagrams, and then various beams and various loads. Whenever different loads acting on different beams, so how to draw the shear force and bending moment diagrams we have learned. So in this today's session, so I want to discuss about the principal stresses. So these principal stresses, part 1, today we will see, and then continuation parts also we will discuss later. So before entering into the topic, we should know about course outcome. In course outcome, the CO3 related to today's topic. At the end of this topic, the student should be able to demonstrate the principal stresses, principal planes, and torsional stresses acting on any arbitrary plane within a structure using analytical and more circle methods. So in this outcome, we will study about principal stresses and then principal planes and the torsional stresses acting on arbitrary plane, and then using the analytical method, the more circles method. So analytical methods and graphical methods we will study in this outcome. So first of all, we should know about principal stresses. So how do you define the principal stresses and the principal planes, and how to calculate those stresses? So we will see in this session. So first of all, we should know the principal stresses and strains. What do you mean by principal stresses and strains? So normal stresses and strains already we have seen, we have discussed in starting earlier sessions. The definition of stress and strain, and what is the relation between these two, stresses and strains, and various elastic constants. The relation between the elastic constants already we have seen. But this is the principal stresses. So what is this? So it is defined as the normal stress calculated at an angle theta when shear stress is considered 0. So normal stress, already you know how do you calculate normal stress. Suppose the normal tensile stress, you can calculate by using empirical relations, load per area. And similarly the shear stress, shear load by shear area. So like this, we can calculate the normal stress. But in this, in principal stresses case, the normal stress calculated at an angle theta, so that is inclination, when shear stress is considered 0. The normal stress can be obtained for maximum and minimum values. Those stresses obtained for maximum and minimum values. So the maximum value of normal stress is known as the major principal stress. Similarly, the minimum value of normal stress is known as minor principal stress. So these two stresses are very, very important while calculating shear stresses and principal stresses and Morse circle method. So the maximum value of normal stress is known as major principal, and the minimum value is known as minor principal stress. See, in this diagram, explain clearly. So when a bar is subjected to tensile load, this bar is subjected to load uniaxial stress. So uniaxial to, so it's x direction and y direction stresses. See, in this diagram shown this sigma x and sigma y. These two are normal stresses, principal uniaxial stresses. So acting at an angle theta. So this is sigma normal. The normal stress is acting theta with angle to this plane. So whenever, see in this diagram shown the plane is with an angle theta. So without angle you can calculate by using empirical relations, but whenever this plane is inclined to the reference line with angle theta, so here the normal stress, the major normal stress is called principal stress. Normal stress is called as major principal stress. The minimum value is called as minor principal stress. So shear stress you can see here in xy plane and yx plane. You can see the normal stress, the normal plane in inclination plane, the shear stress shown in this diagram. See here theta is the angle to what are defined as the principal planes. So these are the planes where the maximum or minimum normal stresses occur, and these stresses are defined as principal stresses. So already have seen in previous slide where the maximum and the normal stress occur. Those stresses are called as principal stresses. See in this the plane shown here with an angle theta. Theta is here 45 degrees. So without angle, so you can draw like this the diagram. So sigma, that is uniaxial stresses, and so uniaxial stresses means x direction and y direction. But this is acting inclined to this line with theta angle. So then you can draw diagram like this. So these two stresses are principal stresses. See, stresses induced due to uniaxial stress on an inclined plane. To obtain a complete picture of the stresses in a bar, we must consider the stresses acting on an inclined as opposed to a normal section through the bar. See, in this diagram, the bar is subjected to tensile load. The load is tensile. So this is normal section. So normal section, but whenever you considering the stresses acting on inclined plane, so inclined plane is opposite to this plane. So this is the inclination. So inclination how much here? Theta. Suppose here you can see this angle is theta. So this is shown here inclined section and then normal section. So in this, because the stresses are the same throughout the entire bar, there is no disturbance. The stresses on the sections are uniformly distributed. See, in normal section, or inclined section, the stresses are uniformly distributed. Suppose in this in 2D view, the one one end to another end, the the force carrying lanes are in uniform. So based on this, we have derived the empirical relations. See here, inclined section, the stress distribution lines are uniform. So uniformly distributed. So here, 2D view for normal section. So here already I told you here drawn the 2D view. So once again see clearly here 2D view of normal section. So whenever the bar is subjected to tensile load, so here the area of the bar, and these are the force carrying lines. So that is stress distribution lines. So the stress distribution lines are uniformly carrying. So there is no disturbance and in this bar. Why? Because there is no irregularity. Suppose the bar is like this. So there is irregularity. So the force distribution lines are not in uniform. So stress concentration will be occurred at this those sections. But in this there is no stress concentration. So in this case, we have derived equations. So that is the stress is equal to load per area. So normal section, wherever you taken the section there, that area you should calculate and substitute in this. You will get the normal stress. See here the inclined plane 2D. So in this also the stress distribution lines are in uniform. There is no diversity. But in this the calculation we using here area, the tangential area. So the inclination area. So this area you should calculate. So in this, in the previous case, the cross section is circle bar. But in this elliptical shape, so that is elliptical shape is the bar. So you should substitute calculate this area and then you will get the normal stress on an inclined section, inclined plane. So specify the orientation of the inclined section PQ. Here shown the inclined section is PQ by the angle theta between the x-axis and normal to the plane. So this is x-axis and this is normal to the plane MN. So the angle theta between the x-axis and then MN. X-axis and MN. Clear? So now in this diagram shown clearly normal and tangential forces, the force resolved into two. So normal force and tangential force. So why? Because the acting and any inclination due to the inclination. So the force P can be resolved into components normal force and perpendicular to the inclined plane, that is n. What is the n? N is equal to p cos theta. Tangential force tangential to the inclined plane, that is p sin theta. One is p cos theta here, normal force, and p sin theta. P cos theta and t is equal to p sin theta. Okay, so here the force calculated by using resolving of forces. Clear? So one is p cos theta and p sin theta. So these force components n and t give rise to normal stress and tangential stress respectively, which are uniformly distributed over the inclined section. So these two forces, normal stress sigma n, you can calculate normal stress sigma n is equal to normal force by area. Clear? So similarly, normal stress and tangential stress, that is sigma n and sigma t. So n by area here, tangential force by area. So the area of section of PQ, AT or APQ, that is equal to mn by cos theta. Here see, here you can see here in this diagram, the area of the PQ, mn by cos theta is equal to a secant theta. Where area of section mn is or an is equal to a normal section, the area is a. See in this diagram shown, the mn and PQ. So here tangential stress and normal stress. One is tangential force, and the force is resolved into two components on this PQ plane with the angle theta, so that here normal stress and normal tangential stress and normal stress you can calculate on this particular plane. So now calculate normal stress. Already I told you the normal stress you can calculate by using this normal force by area, the cross section, the section of PQ area. So now the sigma n, the normal stress, is equal to normal force by area of the PQ. So the area of the PQ is equal to area of the PQ plane. Already mn by cos theta. So mn by cos theta you can write mn secant theta. That is the mn is equal to a, the area of the PQ section. So that the n, the p cos theta by a cos theta. So you will get p by a cos square theta. So you can multiply with cos theta, or 1 by cos. You can write here this equation p cos theta by a by cos theta. So now p by a cos square theta. So that is shown here in this equation. So you can write here p by a cos square theta is equal to, what is p by a? Stress. That is in x direction, uniaxial direction, that is stress load upon area. So sigma cos square theta. So the normal stress is equal to stress acting unique stress multiplied with cos square theta. Similarly, calculate tangential stress. In tangential stress, here P sin theta, the tangential force, by A PQ. Again, secant theta. Now you can write here P sin theta by A by cos theta. That is equal to P sin theta into cos theta by A. So again, you can write in place of P by A sigma sin theta into cos theta is equal to, so you can write in terms of sin 2 theta. So you know sin 2 theta sin 2 theta is equal to 2 sin theta cos theta. So here you can write here in the form of sin 2 theta sigma by 2 sin 2 theta cos theta. So sigma by 2 sin 2 theta. So in place of 2 sin theta cos theta, you can write sin 2 theta. So now calculated the normal stress and tangential stress. So normal stress occurred sigma cos square theta, tangential stress sigma 2 sin 2 theta. So the resultant stress due to the uniaxial stress on the inclined plane. So how do we calculate the resultant stress? The resultant stress is equal to square root of normal stress square plus tangential stress. So here normal stress already we calculated sigma cos square theta, and tangential stress also sigma by 2 sin 2 theta, and substitute here, and after simplification you will get sigma cos theta take outside and cos square theta sin theta. So the square root of cos square theta plus sin square theta is equal to 1. Actually, the cos square theta plus sin square theta is equal to 1. So now substitute in this, the square root of 1 is equal to 1. So that you will get sigma cos theta. Therefore, the maximum tangential stress at 45 degrees and 135 degrees occur. The maximum stress. So cos 45, 1 by root 2. So similarly occurred at 135. Clear? So here calculated tangential stress. So the normal and shear stresses on inclined planes for uniaxial loading here C. So we have calculated the tangential stress occurred at 45 and 135. So tangential stress formula sigma by 2 sin 2 theta, and sigma tangent normal stress is equal to sigma cos square theta. So in this, see, normal and shear stress on inclined planes for uniaxial loading shown here, the sigma is equal to P by tangential stress into cos square theta, and similarly the shear stress is equal to P by 2a into sin 2 theta. Actually, the shear stress occurred at this inclined plane. See, the normal stress sigma at by cos theta. So here sigma at. So see here shear stress tangential sigma by 2 sin 2 theta. So in this you can write normal stress A sigma at by cos 2 theta, and vertical force that is shear stress at by cos theta. that is transverse area. Transverse area. Clear? So the area, so here shown. So this is this is used while calculating the shear stress. So you can write now the shear stress is equal to P by A 2AT sine 2 theta. So you can write the shear stress uh, again this AT you know P by 2 AT n cos theta sigma into sine 2 theta. So again you can substitute these 2 in this. So like this also you can calculate the sigma and shear. See the stress induced due to this initial stress. So on this inclined plane, so the sigma max is equal to 2 mod shear max. So you can see a shear max is equal to 2 times of shear max. So sigma max is equal to 2 times of the shear. So here the sigma max occurs, the theta is equal to 0 and 180. The shear max occurs if theta is equal to 45 and 135. Already we have derived in this at this the tangential stress. Then nothing but the tangential stress is shear stress occurred at 45 and 135. Clear? So that here the sign of shear stress changes for theta greater than 90 degrees and the shear force vector changes direction. So this shear force vector shown in this diagram, the changes its direction. For uniaxial loading, finally the maximum normal stress, the maximum stress is equal to 2 times of the shear stress. So that shear stress is equal to the shear maximum is equal to sigma max by 2. So that is half of the sigma max. See, in this diagram shown the inclination plane and then the the vector notation also shown. See, the two perpendicular normal stresses accompanied with the state of simple shear. So here the diagram shown two perpendicular normal stresses. So P1 and P2, and Q is the shear and normal stresses. So it gives the simple shear stress. So in A, B, C in this plane, the first plane, second, and the third are bottom 4 and 5 and backside 6 planes are there. So take one plane, first plane, and draw this diagram. Take this one. So here shown clearly the element is like this. You take an element like this and then stresses acting on this element. Whenever this the stresses are acting on inclined plane, the theta. So here element stresses shown and the forces. So what are the forces acting? Clear? So here normal stress, normal force and the tangential force, you know. So here calculate the Pn is equal to nothing but here sigma n, and P1 is equal to sigma 1, Pt is equal to sigma 2 and Pt is equal to sigma t. So whenever you are calculating here stress and inclined plane. Pn is into AC on this at this plane. So Pn nothing but sigma n AC. So clear. So similarly, here also calculate here shear stress QBC and QBAB on this plane, on this AB plane, the AB plane, the QAB, and then QBC. The inclination occur at this AC plane only. So considering unit thickness and resolving forces perpendicular to AC. So take this AC plane. So consider this AC plane. We are calculating normal stress accompanied with state of simple shear whenever these stresses plane acting with angle theta. So that here we take that AC and sigma n AC and then sigma 1 B AB and sigma 2 BC. So this force is resolved into two components, that is BC QAB in terms of shear stress QBC. From lower triangle, so take this lower triangle, the cos theta is equal to sigma n AC by sigma 1 AB. So take this is a lower triangle. This is upper triangle. Upper triangle and then lower triangle. So from lower triangle, consider this diagram. So once again draw this lower triangle. Sigma n AC theta and sigma 1 AB. So the cos theta is equal to sigma 1 AC by sigma 1 AB. Cos theta is equal to, what is sigma n AC by Q? The sigma 1 is Q. QBC in terms of shear stress QBC. So then the sigma n AC is equal to sigma 1 AB cos theta plus QBC cos theta. Or you can write sigma n is equal to sigma 1 AB by BC into cos theta plus Q into BC by AC into cos theta. From the triangle, the cos theta is equal to AB by AC and sin theta BC by AC. Now substitute the AB by AC. AB by AC is cos theta. So substitute in this equation, sigma 1 AB by AC is equal to cos theta. So cos square theta, cos theta into cos theta multiplied with cos theta plus Q sin theta. BC by AC is equal to sin theta. So Q sin theta into cos theta. So write like this equation. From upper triangle, you can write sin theta is equal to sigma n AC by sigma 2 BC. The upper triangle, the lower triangle, the upper triangle, you can take this upper triangle and then the sin theta is equal to sigma n AC by sigma 2 BC and sin theta sigma n AC by Q. So you can write the sigma 2 BC is equal to QA. So sigma n AC is equal to sigma 2 BC sin theta plus QAB sin theta. So you can write the sigma n is equal to sigma 2 BC by AC sin theta plus so in this the cos theta is equal to AB by AC and sin theta is equal to BC. So substitute in this equation. So you can write this one sigma n is equal to sigma 2 BC by AC is equal to sin theta into sin theta plus Q AB by AC. AB by AC is equal to cos theta into sin theta. So now you can write sigma 2 sin square theta plus Q cos theta into sin theta. Clear? So one equation, two equations are occurred. So in first equation, taken a lower triangle. For upper triangle, taken upper triangle for write this equation. So they had these two 1 and 2 equations. The sigma n is equal to sigma 1 cos square theta, sigma 2 sin square theta, the q sin theta plus q sin theta plus cos theta. So in this add these two, the sigma n. So here sigma 1 cos square theta plus sigma 2 sin square theta plus q sin 2 theta. So here, so this after adding these two, 2q sin theta cos theta. So we can write in the form of sin 2 theta is equal to 2 sin theta to cos theta. Clear? So here the equation written like this by using this sin 2 theta form. So now finally occurred the equation sigma 1 cos square theta plus sigma 2 sin square theta plus q sin 2 theta. So the above equation can be expressed in an useful alternative form by using the following trigonometrical identities. See the cos square theta is equal to 1 by 2 into 1 plus cos 2 theta. Sin square theta is equal to 1 by 2 into 1 minus cos 2 theta. And sin theta cos theta is equal to 1 by 2 sin 2 theta. So yes, why? Because sin 2 theta is equal to sin 2 theta is equal to 2 sin theta cos theta. Okay. So sin 2 theta you can write by 2. So finally substitute in this equation 1 by 2 into sigma 1 plus sigma 2. So in place of cos square theta substitute this one, and sin square theta write like this, and sin 2 theta you can write 1 by 2 sin theta cos theta. So 1 by 2 sigma 1 minus sigma 2 to cos 2 theta and thus q sin theta. So similarly resolving the forces along AC in AC plane. So in AC plane the forces are resolved sigma 2 BC and sigma 1 AB is 2 AB. Similarly sigma 2 AC and sigma 2 AC resolve the forces along AC plane. So here also same, take the lower triangle and upper triangle. So take lower triangle, the sin theta is equal to minus sigma theta. This one is here lower triangle and this one is upper triangle. So sin theta is equal to minus sigma t AC by q BC. Then sigma t AC is equal to sigma 1 AB into sin theta plus q BC sin theta from the diagram. So in this from the triangle you can write cos theta is equal to AB by AC and sin theta is equal to BC by AC. Now substitute AB by AC in this equation, so you will get the sigma 1 is equal to minus sigma 1, sigma t is equal to minus sigma 1 cos theta into sin 2 theta minus q sin square theta. So similarly, take a upper triangle. So calculate tangential stress, that is cos theta is equal to, you can write like this, sigma t into AC from the upper triangle by sigma 2 BC. Similarly, cos theta sigma TAC by, in place of Q2, QAB. So here write sigma T tangential stress multiplied with AC is equal to sigma 2 BC into cos theta plus QAB cos theta. Or sigma T is equal to Q2 sigma 2 BC by AC cos theta plus Q into AB by AC into cos theta. From the triangle, you can write again the cos theta and sin theta AB by AC, AB by AC, and then sin theta is equal to BC by AC from this triangle. So now substitute these two in this equation. So you will get sigma t is equal to sigma 2 sin theta into cos theta plus q into cos theta. Now add these two equations. We got two equations. One is tangential stress for lower triangle, tangential stress for upper triangle. Add these two. So you will get the tangential stress in terms of sigma 1 and sigma 2 into sin 2 theta plus q cos theta. Now resultant stress is square root of normal stress square plus tangential stress. So here see the normal stress calculated earlier, sigma n. So this one, so now this normal stress, sigma 1 cos square theta plus sigma 2 sin square theta plus q sin 2 theta, substitute in this equation, in this resultant. So the final resultant stress, normal stress and then tangential stress, you will get the resultant stress. So like this, we need to calculate normal principal stresses, the maximum and minimum stresses on inclined plane. So these are the references I have taken. So as Ramamrutam. So the title of the book is Strength of Materials, publishers Dhanpatrai, and the edition 2014. You can take a recent one also. Here the Rajput, R.K. Rajput, Strength of Materials. Title of the book, Strength of Materials. And R.K. Bansal, the title of the book is Textbook of Strength of Material, publications, Lakshmi Publications. Similar R.S. Kurmi Gupta. So the Strength of Material title of the book is Strength of Material and the publishers are. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.